Okay, hello everyone. So today we will learn about continuous probability distribution. So the learning objective for today will be to convert a normal distribution to a standard normal distribution. And then next to determine probabilities using the normal distribution, to understand the concept of a sampling distribution, and lastly to find the probability of the sample mean. Okay, so this one is like preview. So right now we are learning about probability distribution. So last week we looked at discrete probability distribution. So we learned about two special discrete distribution, which is binomial distribution and Poisson distribution. So today we will learn about continuous, which is normal distribution. Okay, continuous probability distribution. So this distribution describes the probabilities of all possible values within a given range for a continuous random variable. Okay, the variable can take on any value within its range, not just specific value. So the keyword here is within its range. Okay, so not just specific value. Okay, and then the example of continuous random variables are height, weight, temperature. Okay, and then continuous probability distribution are often described by probability density function. So we call as PDF, or this one is f of x. Okay. So this is the difference between discrete and continuous. So variable type, for discrete we will have the discrete random variable. So we have a specific separate values, and this one can be like countable. Okay, and then for variable type, for continuous, so the random variable will be continuous, which is any value within a range. Okay, and then the example for discrete is like number of successes, number of defective items, and then for continuous we can have like height, weight, temperature, distance. Okay, and then for graph, for discrete we can have a list of values and probabilities. So this one we can put in table because we have separate values for random variable, and then we can also do a bar chart for this discrete. Okay, for continuous, so this one will be a smooth curve. So since we have probability density function f of x, so we can make a smooth curve for this f of x. Okay, and then for probability for discrete, it is assigned to each specific value. Probability of x equals to x. So for example, if you want to find probability of x from 1 to 2, so this one is actually equals to probability of x equals to 1 plus probability of x equals to 2. This one just for example. For continuous, we cannot find probability of x equals to x, but we can find probability of x within a range. So for this one, let's say we have x between xa to x2. Okay, so this one is within a range, but if you want to find probability of x equals to some value, let's say x, this one will be equals to 0. You cannot find for continuous. Okay. So for this one, let's say we want to find probability of x between 1 and 2. So basically, finding the area under the curve, and then we will integrate the probability density function to find the probability. So this one equals to integrate from 1 to 2 f of x dx. So the common distribution for discrete function is like binomial, Poisson, multinomial, and then for continuous, we have like normal, and then student's t distribution, and a uniform chi-squared. Okay, but for this one, for today's lecture, we only look at normal distribution. So what is normal distribution? So this one is known as the quotient distribution. So it is a bell-shaped probability distribution that is symmetric about the mean. So the keyword here is the bell shape and also the symmetric about the mean. So normal distribution is used to model many natural and social phenomena. So for example, the height and weight distribution of the population. So this one is normally distributed. Okay, and then the probability density function, the f of x for normal distribution is this one. It looks complicated, like 1 over square root 2 pi sigma squared, and then e to the power of minus x minus mu squared over 2 sigma squared. So for this one, the mu is the mean, and then the sigma is the standard deviation. Okay, so that means if you want to find probability of x in between 1 to 2, this one is actually equals to integrate from 1 to 2 f of x dx, which is integrate from 1 to 2, 1 over square root 2 pi sigma squared e to the power of minus x minus min, s minus mu squared over 2 sigma squared dx. So this is how we find probability when it comes to continuous distribution. Okay, so let's look at characteristics of the normal distribution. So first, it is bell shape. So we have this bell shape, bell curve here. So what does it mean by bell shape? The mean, the median, the mode is equal. Okay, so over here, the middle here will be the mean, the median, and the mode. Okay, and then second characteristic is it is symmetrical about the mean. So a normal distribution can be divided through the mean. So the mean is over here, mu. And then it can be divided through the mean into 2 equal half, and this half possess exactly the same shape. So this one is the same shape as the right one. And then if you calculate the probability here, this one will be 0.5, the probability, and then the right one also is 0.5. Okay, remember the probability will be the area under the curve. Okay, for continuous. And then the third characteristic is it is asymptotic. So what does it mean by asymptotic is the tails, which is this one, approach the x-axis but never actually touch the x-axis. Okay, we will always like this. It never really touch the x-axis. So this is what it means by asymptotic. Okay, and then the fourth one, a normal distribution is completely described by its mean and standard deviation. So when we say normal distribution, so we have x is like this one, this symbol, and then we have the mean and also the standard deviation. So the mean will be the middle point here, the one divide this curve into two symmetric curve. Okay, and then the standard deviation is actually this one, the variation around the mean. Okay, so this one is standard, this one is the sigma, the distance here. Okay, and then the distance from here will be 2 sigma, and then here will be 3 sigma. Okay. Okay, so this one is like the characteristic of normal distribution. This one is always true for any normal distribution. So let's say this one is the mean, the middle here, and then this one is sigma. So this one, so there are 68% of the observations lies between mu minus sigma and mu plus sigma. So mu over here will be mu plus sigma, and then over here will be mu minus sigma. So basically, if we take this one, mu minus sigma to mu plus sigma, so 98% of the observation will be between these two values. So that means the probability under this curve will be 0.68, and then there are 95% of the observation will lie between mu minus 2 sigma plus and mu plus 2 sigma. So this one is actually this one. So let's say we have over here mu minus 2 sigma, and also over here mu plus 2 sigma. So the probability between these two is 0.95. Okay, and then the third one, there are 99.7% of the observation lies between mu minus 3 sigma to mu plus 3 sigma. So from here to here will be 99.7%. Okay, so this one. So when I say the normal distribution is characterized by the mean and the standard deviation, so this is what it means. So for example, this one, the purple one, so the mean is 30, and then the standard deviation is 5. So the mean here will be at 30 here, and then the standard deviation is actually the variation around the mean. So the variation around the mean is 5, so it's quite thin here. Okay, and then compared to this one, the green one, so the mean is 50, so that's why we have over here 50, and then the standard deviation is 6. So this one will be bigger than 5. So that's why the variation here is like thicker than this one. Okay. Okay, and then, okay. So what is the difference between before before this is like normal distribution. Right now we are looking at standard normal distribution. So when we say standard, this one normally we use the Z instead of X. Okay, standard normal distribution has mean equals to 0 and standard deviation equals to 1. Okay, also called as Z distribution. So this one we always have this one. Z is normally distributed with mean equals to 0 and standard deviation equals to 1. Okay. So now since we have Z, so over here we'll have the Z values. So the mean is 0 and then this one is the standard deviation. Okay, so remember the probability between mu minus sigma to mu plus sigma, this one will be 0.68. Okay, and then this one is the mu minus 2 sigma, mu plus 2 sigma. Okay, so this one is the standard normal distribution. Okay, so basically why we learn about standard normal distribution is because any normal probability distribution can be converted into standard normal probability distribution. So basically any x with mean equals to mu and standard deviation sigma can be converted into z, which is a normal distribution with mean 0 and standard deviation 1. So how we convert is that, so first the x, we minus the mu, the mean, and then we divide by standard deviation. So basically the mean here, we need to shift to 0. So that's why we minus the mean. And then over here, the standard deviation here, we need to scale to 1. So that's why we divide by sigma to get the variation here is scaled to 1. Okay, so whenever we do this operation, the x will become z. So if you notice here, this one, the x, this one is x values. When we convert to z, over here will be z values. Okay. So this is once we do the standardization. So the normal distribution, any normal distribution will become standard normal. And then the x value will become z value. And then the x normally distributed with mean mu and standard deviation sigma will become normally distributed with mean 0 and standard deviation 1. Okay. Okay. Why do we learn about the standard normal distribution? Okay, the reason is because the standard normal distribution, this one, we already have table for the probability of z. Okay, so we can just use the table to get the probability instead of we use the integrate from a to b f of x dx, the one I showed you before this. So this one is so complicated because we have to integrate. So instead, for any x that is normally distributed, so we convert first to the standard normal distribution z, and then to get the probability we just read the table, the standard normal table. Okay, example. So let's look at example. So the playing life of a radio has normal distribution with mean 600. So this one is the mu. And then standard deviation 100 hours. So this one is the sigma. So we have x is normally distributed with mean 600. And then sigma is 100. And then convert the following x values to z values. So we just need to use the formula. So we know z equals to x minus mean over standard deviation. So we use this formula. So for A, so the playing life of 700 hours. So now x equals to 700. So the z values will be 700 minus the mean, which is 600, divided by standard deviation, which is 100. So we get z equals to 1. And then B, the playing life of 550 hours. So S equals to 550. So the z will be equals to 550 minus 600 and then divide by 100. So this one, the z equals to negative 0.5. negative 0.5. Okay, now we want to learn about probability of observation lies between two values. Okay, so let's say we want to find probability of x in between A to B. So we have A over here, we have B over here. So for continuous, we know the probability will be the total area under the curve. So this one is actually the total area under this curve. This one, the shaded region here. So if you want to find this probability, it's actually the area under this curve. Okay, and then let's say we want to find probability of x less than A. So let's say A is over here. So less than A will be area under this whole curve here. So meaning that the curve is actually shaded from negative infinity to A. Okay, and then if probability of x greater than A, so if we have A here, so the area is actually from A to positive infinity. So this shaded region here. Okay, now we want to learn how to find probabilities using the Z table. So the tabulated areas under the Z table are actually probabilities of interval extending from the mean, which is Z equals to 0, mu equals to 0, to the point Z to its right. Okay, so basically, the probability using the Z table is this one. Probability of Z from 0 to Z. So the area from 0 to positive infinity, the right side is actually 0.5, and the area from minus infinity to 0, which is this one, the left side here, is 0.5 because the curve is symmetric. Okay, so if let's say A is any positive number, so probability from Z from 0 to A, which is this one, the blue area here, is also actually equals to this one, probability of Z from negative A to 0. So let's say we want to find this probability from minus A to 0. So we draw this curve, bell curve. So the negative A is over here. So actually we want to find this probability. And since this is symmetric, so this one is actually equals to this one. Okay, that's why we have this equation. Okay, and then to get this, you just straight away find from the table Z equals to A to get this probability. Okay, later I will show you how to read the table. Okay, now let's say we want to find this probability. So basically probability of Z from minus A to A. So it's actually these two regions, the yellow region and also the blue region. Okay, so this one is equals to probability of Z from negative A to 0, which is the yellow region, and then plus probability of Z from 0 to A, which is the blue region. And this one can read from the table. And then since this one is equals to probability of Z from 0 to A, so that means this one we just multiply by 2. Okay, so this one equals to 2 times probability of Z from 0 to A. Since it is symmetric, so the value of the probability is the same. Okay, so the yellow and the blue region, the probability is the same. So let's say now we have A, so we want to find probability of Z greater than A. So basically this one, the yellow region here. Okay, and then we know this whole thing, the probability on the right side of the mean is equals to 0.5. So for this one, it's actually equals to 0.5 minus the probability of Z from 0 to A, which is minus the blue region here. And then this one, read from the table. Okay. And if you want to find this one, probability of Z less than negative A. So let's say negative A is here. So less than will be to the left of this. Okay, whenever we want to find probability on the left side of the mean, which is the negative region, so we can actually the easiest way will be we reflect that region to the positive side. So this one, we draw the positive side A. So basically the property is this region, which is the probability of Z greater than A. So reflect this, only then we can find the probability. So now, let's say we want to find probability of Z less than A. So A is over here. So this one is actually all, the yellow region plus the blue region. And then we know the yellow region here, the probability is equals to 0.5. So that's why this one equals to 0.5 plus probability of Z from 0 to A. And then this one read from the table. Okay, and then this one is also equals to this one. Let's say we have negative here, negative A here. And then we want to find probability of Z greater than negative A. It's the same. Okay, which is this one. Okay, so this is how we read the table. Okay, so let's say we want to find, okay, let's say A equals to 1.96, and then we want to find probability of Z from 0 to 1.96, which is this region, the red region here. So the way we read, so we look the first column here, the Z here. So we find 1.9. So 1.9 is here. And then look at this one, the first row. So for the first row, we only look at the last digit here. So the last digit is 6, so we look at 0.06. So then 1.9 plus 0.06, we get 1.96. So this is the probability. The probability is equal to 0.475. Okay. So basically, this is the table. So I put here. So it is easier for you guys to refer the table. So basically, the normal table here, I put at the end of this lecture slide. Okay, the complete table. So you can refer to that table as well. Okay, let's say now A is 1.96. So we want to find probability of Z from 0 to 1.96. So whenever we have this, I suggest you to draw the bell curve. Okay, draw the bell curve. And then we put the 1.96 here. And then we want probability from 0 to 1.96. So basically, we want this probability. Since we want this probability, then we can straight away find from this table. So 1.9 is over here. And then 0.06 over here. So basically, this one is this value. So this one is equals to 0.4750. So this one I already showed last time. So let's say we have the negative 1.96. And then we want to find probability from negative 1.96 to 0, which is this one. Which is the same as this one. You just reflect to the positive side. Okay, now let's look at the next one. So we want to find probability of Z between negative 1.96 to 1.96. Okay, and then this one. So let's draw the bell curve. So we have this bell curve. So negative 1.96 is over here. And then 1.96 is over here. So we want to find the probability in between. Okay, so that means we want to find probability of Z in between 1.96 to 0, which is this part, plus probability of Z from 0 to 1.96, which is this part. Okay, and then the second part, this one we can get from table. Okay, and then this one over here is actually the same as the right side. So that's why this one is 2 times the value from the table. And then the value from the table is 0.475. So the answer here is equals to 0.95. Okay. So let's look at next. So this one we want to find Z, probability of Z greater than 1.96. So we draw the bell curve. So we have over here 1.96. So we want greater than this. So basically we want this one. Okay, but remember the one from the table is actually this one. The one from the table is this one, from 0 to 1.96, from 0 to z. And then we know the total on the right side here is 0.5. So that's why for this one, the probability here is equals to 0.5 minus probability of z from 0 to 1.96. And then this one we can get from the table. So this one equals to 0.5 minus 0.475. So this one 1.96. Okay. And then the answer here is 0.025. So we do the same for this one. We draw the bell curve first. So we have negative 1.96, and then we want probability of z less than this one, which is this one. And then remember, whenever it is on the negative side, so we reflect that to the positive side. So we have 1.96 here, and then we want this probability, which is the same as this one. So the answer here is 0.025. Okay, so the next one, we want probability of z less than 1.96. So we draw the bell curve. So over here is 1.96. So we want less than this value. So basically we want this one. Okay, and then we know the left side here, the probability is 0.5. And then we know this one actually we can get from table. So this one is equals to 0.5 plus probability of z from 0 to 1.96. So this one is from the table. So this one equals to 0.5 plus 0.475. Okay, which is equals to 0.975. So next one, we draw the bell curve. So we have negative 1.96 here. So we want probability greater than. Okay, again, this one we can reflect to the positive side. So we reflect to the positive side. And then this one is the 1.96. And then instead of greater than this, is actually the less than this. Okay, which is the same as the first one. So this one is 0.975. Okay, so brief review, just a summary of everything that I just taught just now. Okay, so to find the area between 0 to z, so this one you can look up the value directly in the table. Okay, if you want to find probability of 0 to z. So basically this one is only this. So let's say z is the positive value here. So we want to find this probability. So look directly from the table. Okay, number 2, to find the area between 2 points on different sides of the mean. So determine the two values and add the corresponding areas. So this one is actually, we have this. So we have like A and B on 2 different sides. Okay, and then this one, we can look directly from the table. Okay, and then this one, A is negative, so we can reflect to the positive side. Also, we can look directly from the table. Okay, so basically this one is actually equals to probability of z from 0 to b plus probability of z from 0 to a. Okay, this one is actually negative a. Okay. And then for 3, to find the area between 2 points on the same side. Okay, and then determine the two z value and then subtract the smaller from the larger area. So this one is actually, we have the same side. So let's say we have A here and then we have B here. So we want to find probability in between these. So this one is actually probability from 0 to b, the larger one, probability of z from 0 to b, minus probability of z from 0 to a. So this one can look directly from the table. Okay, and then last one, to find the areas beyond z, like greater than z or less than z. So locate the probability of z in the table and subtract that value from 0.5. So this one is actually this one. This one is the number 4. So let's say we have z, so we want to find this one beyond here. So it's like 0.5 minus this value, which is can look directly from the table over here. Okay. So this is example on how to find the probability using Z table. So for A, we want to find probability between 0 to Z, 0 to 1. So this one is actually probability of Z from 0 to 1. So we draw the bell curve. So we have 0 and then we have 1. So we want this probability. So basically this one just look directly from the table 1.00. So this one is 1.0 and then this one is 1.00. So the probability here equals to 0.3413. Okay, and then this one we want to find probability of Z between 0 to -1, or it's actually -1 to 0. Okay, probability of Z from -1 to 0. So we draw the bell curve. So -1 is here, 0 is here. So we are actually want to find this probability. So again, since this one is in negative region, so we reflect to the positive region. So we have 0 and then we have 1. So we want to find this probability, which is the same as A. Okay. So next, we want to find probability of Z above 1.35. So probability of Z greater than 1.35. Okay, so we draw the bell-shaped curve. So let's say this one is 1.35. So we want probability of greater than this. Okay, and then we know everything here is 0.5. So this one is actually equals to 0.5 minus probability of Z from 0 to 1.35. Okay, and then this one, which is region here, we can find the probability from the table. So this one equals to 0.5 minus. So let's look at 1.35. So we have 1.3 over here, and then we have 0.05 over here. So the value here is this one. So this one equals to 0.4115. So 0.5 minus 0.4115. So this one we get 0.0885. Okay, now this one is probability of Z below, which is less than -1.35. Okay, this one is equals to, okay, this one is -1.35. So we want to find this probability, and then we can reflect to the positive side, which is this probability. And this one is the same as C. Okay, I forgot to mention. So for continuous, the equal sign here does not really matter for continuous. Okay, for discrete, the equal sign is very important, but for continuous, the equal sign does not matter. Okay, it will be the same, equal sign or don't have the equal sign. Okay. Okay, and then E, we want to find probability of Z in between 1 to 1.35. So this is when the value of Z is on the same side of the mean. Okay, let's draw the bell-shaped curve. So we have 1 and then 1.35. So basically we want this probability. Okay, so this one actually we have to subtract. So the larger area minus the smaller area. So the larger area, the green, which is probability of Z from 0 to 1.35. Okay, and then minus the smaller area. So the smaller area is actually this one, the one in red, to get the blue region. So the one in red is actually probability of Z from 0 to 1. So once we have this form, you guys can look the value here directly from the table. So probability, okay, 1.35, we have this one. So 0.4115 and then minus. So for 1, we have this one. 1.00 is this one. 0.3413. So this one equals to 0.0702. Okay, for F, we want to find probability of Z in between negative 1.35 to 1. So we draw the bell-shaped curve. So negative 1.35 and then, sorry, this one is negative 1. And then this one over here will be negative 1. So we want this one. So again, we reflect this region to the positive side. So we have 1 and then we have 1.35. So we want this region, which is the same as E. Okay. Okay, and then this one, we want to find probability of Z in between negative 1.35 to 1. So we draw the bell-shaped curve. So negative 1.35 to 1. So this is when the Z is not on the same side of the mean. So one is on the negative side and the another one is on the positive side. So we want this probability in between. So this one is actually this probability on the left side plus probability on the right side. So the probability on the right side is actually probability of Z from 0 to 1, which you can look at from the table. And then plus, so probability on the left side, actually we can reflect to the right side. So this one equals to probability of Z from 0 to 1.35. And then this one, both we can look at from the table. So the one is this one, 0.3413, and then plus 1.35 is this one. 1.3 and then 1.35. 0.4115. So this one is equals to 0.7528. Okay, so the last one here, we want to find probability of Z in between negative 1.35 to 1.35. So again, this one also is not on the same side. So we have this one. So we draw the bell-shaped curve. So we have negative 1.35 and then this one also 1.35. So we want the probability in between. Okay, and then this one, since the value is the same, 1.35, so this one, the left side is actually equals to the right side. So this one equals to 2 times probability of Z from 0 to 1.35. So this one is 2 times 0.411. which is equals to 0.823. Okay, let's look at example. Okay, the example before. So I just use the same example as before. So the playing life of a radio has normal distribution with mean 600 and standard deviation 100. So we have this one, normal distribution. Okay, find the probability that the playing life of the radio is in between 600 to 700. So the playing life, okay, X is the playing life of the radio. So we want to find probability of the playing life of the radio, which is X, in between 600 to 700. And then we know any normal distribution can be converted into standard normal. So this is when we use the conversion. Okay, so we convert this X to standard normal distribution. So this is the formula, Z equals to X minus mean divided by standard deviation. So this one equals to probability of, so 600 minus the mean, which is 600, and then divided by standard deviation, which is 100, and then less than X minus mean over standard deviation, and then less than 700 minus the mean, which is 600 over standard deviation, which is 100. And then you calculate this one and also this one. So this one equals to probability of 0 and then less than, okay, for this one you just put Z, okay, based on this formula. And then less than, so calculate this one, we get 1. Okay, once we have this, we can draw. So draw the bell-shaped curve. So we have 0 and then we have 1, and then we want to find probability in between. So basically this one we can look for this probability directly from the table. So we look for 1.00, which is this one. So this one equals to 0.3413. Okay. Okay, let's look at B. So the playing life of the radio is above 700. So basically we want to find probability of X greater than 700. So again, so we use this formula, Z. So Z equals to X minus mean over standard deviation. So this one is equals to probability of X minus mean over standard deviation is greater than 700 minus the mean, which is 600, divided by standard deviation, which is 100. So this one equals to probability of Z greater than, so when we calculate this, we get greater than 1. And then we draw. So we draw this one. And then we have 1. So we want to find this probability that is greater than 1. So basically this one equals to 0.5, the whole probability here, minus this probability. So 0.5 minus probability of Z from 0 to 1. And then this probability can be read from the table, which is this one. So this one equals to 0.5 minus 0.3413, which is equals to 0.1587. Okay, let's look at C. So we want to find the probability that the playing life of the radio is in between 400 to 700 hours. So we want to find probability of X in between 400 to 700. Okay, again, we convert to standard normal. So this one is 400 minus the mean, 600 divided by standard deviation, 100. And then less than X minus mean divided by standard deviation, less than 700 minus the mean divided by standard deviation. And then we calculate this one. So this one is probability of -2 and then less than Z less than 1. Okay, and then we draw the bell-shaped curve. So -2 is over here and then 1 is over here. So we want the probability in between. So basically this probability on the left side plus probability on the right side. So probability on the right side is probability of Z from 0 to 1 and then plus. So the right side -2 we can reflect to the right side. So this one is actually probability of Z from 0 to 2. And then we can look directly from the table, which is this one, 0.3413. And then plus this one, 0.4772. So this one equals to 0.8185. So every example that I showed just now is actually we want to find the probability given the value of X. Okay, what if it's the other way around? We are given the probability and we need to find the value of X. Okay, so basically it's like this. So we are given the probability, let's say the probability is 80%, and then we want to find what is the value of Z, given that the probability is 80%. Okay, so this one is like finding the value of an observation with a given probability. Okay, let's look at example. Okay, X is a test course, and then X is a normally distributed with mean 75 and standard deviation 8. So the professor wants to award an A to students whose course is in the highest 10%. So for this one, we can draw the bell-shaped curve. So the highest 10% means that the top 10%. Okay, let's say the top 10% will be on the right side here. So let's say we put this one as X. So the top 10%, the highest 10% will be the greater than X. So the probability over here is 0.1. Okay, so we want to find X such that the probability of greater than X equals to 0.1. Okay, so instead of finding X, we will find value of Z. Since we can convert between X and Z, so actually we will find the value of Z. So we want to find value of Z over here, such that the probability here is greater than Z here is 0.1. Okay, let's say I put here Z star. Okay, so we want to find Z such that probability of Z greater than Z star equals to 0.1. Okay, but from the table it's actually from 0 to Z star. So the probability here will be 0.4. 0.5 minus 0.1 will be 0.4. So what we can do is we can look from the table, okay, and then look inside the table here. Find 0.4. Find the closest to 0.4. So if you look at here, the closest to 0.4, I would say this one. 0.3997. So this one will give the value for Z star is 1.28. Okay, let me write it down. So this one is actually the same as probability of Z from 0 to Z star equals to 0.4. So that's why we find the probability inside the table 0.4. So when we find, we get Z star equals to 1.28. Okay, so find closest to 0.4. Find inside the table. Okay, this one is value for Z. But the question are asking for value for X. Okay, remember the conversion. So Z equals to X minus mean divided by standard deviation. Okay, so we use the same formula to get X. So we have the Z, which is 1.28 equals to X minus mean, which is 75 divided by sigma, standard deviation, which is 8. So we find X equals to 85.24. So that means over here is 85.24. So the students who get greater than 85.24 will get A, and the students less than 85.24 will get other grades. Okay? Okay, let's look at B. The same question. So X is the test score with mean 75 and standard deviation 8. So now the value above which 95% of the test scores lie. So this one is if we want to draw. So we have to find X such that probability of X greater than this value X is equals to 0.95. So since the probability greater than X is 0.95, that means we can also write the complement of this one. So probability of X less than X here is equals to 0.05. So this one is small value. So basically this one is actually on the left side of the mean. So this one is the X, such that the probability of less than X here is 0.05. So since this one is on the left side, so this one will be the negative. Okay. Okay, instead of put here X, I want to put here Z, straight away Z. So the Z star here is on the left side, so this one will be negative value. Okay, so now, since this one is negative, we can reflect to the positive side. So we reflect Z star here. Okay, and then over here will be 0.05. So that means in between 0 to Z star is 0.45. So we want to find Z such that probability of Z from 0 to Z star equals to 0.45. Okay, and then we look at the table. The closest one, find the probability inside the table. So the closest one to 0.45. So if you look at this, okay, basically we have two closest one. We have these two. So for this one, you can choose either one. So you can choose either 1.64 or 1.65. Because these two give the same difference when we minus from 0.45. Or actually, you can add these two value, 1.64 plus 1.65, and then you divide by 2 to get the Z value. So either these three. Okay, you can choose either one. Okay, so let's say this one I take 1.65. So this one Z star is equals to 1.65. And then remember the original Z star is negative. So we have Z star equals to negative 1.65. This is the value for Z, but we want the value for X. Okay, again, we use the formula. So Z equals to X minus mean over standard deviation. So the Z is 1.65 equals to X minus 75. Sorry, this one is negative 1.65. Okay, X minus 75 divided by 8. So this gives X equals to 61.8. So that means students, the probability of students with score 61 greater than 61.8 is 95% or 0.95. So we finished the normal distribution. Okay, next we will look at sampling distribution. Okay, what is sampling distribution? What is sampling? So basically, in statistical analysis, sampling is a process of taking samples, which is a group of observation from a larger population. So if we have a large population, so we just only take some of it as samples. Okay, so this is what it means by sampling. So why we do sampling? So it is impractical to measure or test all items in a population because we have like quite a big number, infinite number. So that's why we do sampling. We only took some of it and then measure something. Okay, the purpose of do sampling is to calculate statistics, for example, the mean, standard deviation, and then we can infer something about the population. Okay. Okay, this one is like example of sampling methods. So we can have like simple random sampling, and then we can also have systematic sampling. So the random sampling is just like we pick the item randomly. Okay, and then systematic sampling is like we can, maybe like for each item, we give numbers, and then maybe we can pick like the even numbers of it, or maybe like the hundredth number. So this one is the systematic sampling. Okay, sampling distribution of the mean. Okay, suppose all possible samples of size n are drawn from a normal population and their means are noted. So basically, we have this one, population, a big population. Okay, and then let's say we want to pick sample of n. Sample of size n. Okay, and then to all possible samples, so let's say we can have like sample A, and then we can have sample B, sample C, sample D, and sample E. So these are all the possible samples. This one is just for example, all possible samples. And then for each sample, we calculate the mean. So for this one, we have the mean, x A bar. So this one is x B bar, the mean for sample B. And then for sample C, we have x C bar. For sample D, we have the mean x D bar. And then this one is x E bar. So for each sample, we calculate the mean. Okay, and then all the sample mean from this sample actually will form a sampling distribution known as sampling distribution of the mean. So this mean, we also have their own distribution actually. Okay, if repeated samples are taken from a population and we measure the same statistic, which is mean, so the statistic for each sample will vary, will have different value, and there will have a distribution. Okay, the sample mean itself have their own distribution. Okay, let's look at one example. So sampling distribution of the mean is a probability distribution consisting of all possible sample means of a given sample size selected from a population. So this one is just one simple example. So let's say a population have 6 families. So families is like Andy, Badawi, Chandran, Daud, Elvin, Fong. This one is like A, B, C, D, E, F. So we have 6 families, and we want to measure the number of children. Okay. So like Andy have 1 children, Badawi have 2, Chandran have 3, and then so on. And then for this one, instead of we look at the whole population, so we want to do sampling. So we want to pick only 2 families out of this population. Okay. So for this one, okay, before that, so since this one is the population of 6 families and we look at number of children, so we have this number of children, and then from this actually we can calculate the mean for population, which is mu. So we add all of these numbers, number of children, which is 18, and then divide by 6 because we have 6 families. So the population mean is equals to 3. Okay, and then now we want to do sampling. We want to pick sample of 2. So n equals to 2. So we need to list all the possible samples here. So that means the number of ways to choose 2 out of 6 families is actually this one, 6 choose 2, the combination. So this one equals to 15 possible ways, 15 possible combination. Okay, so this one is actually, I list out all the possible sample actually. So number 1 until 15. Okay, so number 1, the sample consists of family AB, and then number 2, AC, and then AD, AE, and so on. So these are all the possible samples. And then for each sample, I calculate again the number of children for each sample. Okay, so let's say sample 1, we have family AB. So A and B, the total number of children is 2. Okay, and then for sample 2, we have total number of children is 1 plus 3, which is 4. And so on. So we calculate number of children for each sample. Okay, and then again, we calculate the sample mean. Okay. So the sample mean here, so since now n equals to 2, the sample equals to 2, so the number of children now will divide by 2. So the 3 divided by 2, we get 1.5, and then 4 divided by 2, we get 2, and so on. So the sample mean is like the number of children divided by the number of families for this, which is 2. Okay, so this sample mean has their own distribution. Okay, so this is what you mean by sampling distribution of the sample mean. Okay, and then next, so let's say we want to calculate the total of the sample mean. So we add everything. So when we add everything, actually we get the sum of the x bar equals to 45. Okay, and then this 45, now we want to calculate the mean, the average of the sample mean. So we denote as mu sub x bar here. So the mean will be equals to total divided by number of samples. So total is 45 divided by 15. We get the mean equals to 3. So from this example, actually we show that the population mean is equals to the mean of the sampling mean. Okay. So the mu sub x bar is equals to the population mean. Okay, so these are the important features of sampling distribution of the mean. So the first one is, it is approximately to be normally distributed. Approximately, but it's not true for all cases. Okay, but certain cases, yes, it is normally distributed. Okay, and then the mean of the sample mean equals to the population mean. So this one, I just showed using previous example. Mu of the mean of the sample mean, which is this one, we denote as this one equals to the population mean. Okay, and then standard error. Okay, standard error is actually the standard deviation. So standard deviation of the sampling mean. So we denote as sigma sub x bar is equals to sigma divided by square root n. So n is the number of sample. Okay, this is the sampling error or standard error of the sample mean. Okay, it is the standard deviation of the sampling distribution of the sample means, which is this formula. And then we use this symbol. So sigma sub x bar is the symbol for the standard error of the sample mean. And then sigma is the standard deviation of the population. And then n is the sample size, the size of the sample. Okay, this one. There will be less dispersion in the sampling distribution of the sample mean than in population mean. So let's say the population here is this one, the curve. Okay. And then let's say we want to take a sample size of 4. And we know the standard deviation here is equals to sigma divided by square root 4. So since we have divided by square root 4, so the dispersion here will be less dispersion, less dispersed. Okay. And then again, if we take a sample size of bigger sample size, which is 16, n equals to 16 now. So the standard deviation of standard error is sigma divided by square root 16. So this one will have less dispersion. So the bigger the size, sample size, the smaller the dispersion, or the smaller the standard error or the standard deviation of the sample mean. Okay, this one is just the summary. So normal distribution population, so let's say the population is normally distributed. Okay, and then this one is the number of element or the number of population. Okay, and then this one is the sampling distribution of the mean of the x bar. So the number of elements will depends on the sample size. Okay, and then the mean will be equals, the population mean and also the sampling mean will be equals. Okay, and then the standard deviation of the sample mean will be equals to the population standard deviation divided by square root n. Okay, next we will look at central limit theorem. Okay, if a population which does not follow the normal distribution, or actually we don't know the distribution for the population, okay, but the sample size is at least 30, so this one is n, at least 30 means n is greater than or equals to 30, then the sampling distribution of the sample means will approximately follow the normal distribution. So basically this is the summary of the sentence. So S can be any distribution with mean mu and standard deviation sigma. Okay, and then x bar, the sample mean, will be normally distributed with mean mu and standard deviation sigma over square root n if n is greater than or equals to 30. So there is this condition here. So the larger the sample size n, the better the approximation, the better it is converged to the normal distribution. Okay, for a normal population, so let's say x is normal. So we have x is normally distributed with mean mu and standard deviation sigma. Okay, and then the sampling distribution of the sample mean is normally distributed for any sample size. So for this one, we don't really care about n. N is small or large, the x bar will always be normally distributed with mean mu, and then the standard deviation is sigma over square root n. Always be whatever n is, if the population is normal. Okay. So apply the central limit theorem to find the probabilities of selecting possible sample means from a sampling probability distribution. So we will have this one. If it is normally distributed, then we can use the z value of the sample mean. So now this is the formula for the z value if you want to converge this to standard normal distribution. So it's like z equals to x bar minus mu divided by sigma over square root n. Okay, let's look at example. So a normal population, so over here we have normal population, has a mean 60 and standard deviation 12. So we have x is normally distributed with mean equals to 60 and standard deviation equals to 12. And then you select a random sample of 9. So n equals to 9. So compute the probability of the sample mean, this ABC. Okay, since x, the population is normally distributed, so for any sample size n, x bar will always be normally distributed. Okay, so for this one, x bar is actually normally distributed. Okay, and then the mean for x bar is equals to the population mean, which is 60. Okay, and then the standard deviation of the sample mean equals to standard deviation of the population divided by square root n, which is 12 divided by square root 9. So this one is equals to 4. So that means x bar is normally distributed with mean equals to 60 and then standard deviation equals to 4. Okay, so now we want to calculate A. So we want to compute probability of the sample mean. Okay, so we want to compute probability of x bar, sample mean is x bar, more than 63. Okay, and then this one, Since we know x bar is normally distributed, so we can change to standard normal. So this one equals to probability of x bar minus the mean, which is 60, and then divide by the standard deviation, which is 4. And then this one is greater than x bar minus the mean divided by standard deviation. Sorry. Okay, let me do it again. Okay, this one is x bar minus the mean divided by standard deviation greater than 63 minus the mean, which is 60, divided by standard deviation, which is 4. Okay, this one is equals to probability of, okay, over here is standard normal, which is z. Okay, and then greater than, so we calculate the 63 minus 60 divided by 4. So this one we get greater than 0.75. And then we draw the bell-shaped curve. So this one is 0.75. So we want probability of this one. So again, we know from the table is this one. So this one equals to 0.5 minus probability of z from 0 to 0.75. So this one we can read from the table. So this one equals to 0.5 minus 0.2734, which is equals to 0.2266. Okay, so for B, we want to find probability of the sample mean, which is x bar, less than 56. Okay, so for B and C, I want you guys to try by yourself. So I give the final answer. So for B, the final answer is 0.1587. And then for C, we want to find probability of the sample mean in between 56 to 63. So the final answer for here is 0.6147. Okay, and then the okay, so for this one, okay, let's look at this one. I'll just give the distribution and then you can try this yourself. I also give the final answer for this one. Okay, according to a survey, the average annual salary for a graduated student in accounting firm is 97,500. So this one is the average, which is the mean, the population mean. And then with a population standard deviation 30,000, so this one is the standard deviation, population standard deviation. Okay, so from the question, it did not state the population distribution. So we don't know whether it's normal or not. Okay, and then consider a random sample of 40 graduated students. So we have n equals to 40. So instead of looking at the population, the whole population, so we only look at the sample of 40 students. Okay, what is the probability that the sample mean? So we want to find probability of x bar. Is this one, ABC. So x, we don't know whether it's normally distributed, but we do know that the mean, the mu is this one, 97,500, and then the standard deviation is 30,000. Okay, and then we take a sample of 40 students. Okay, n equals to 40. Okay, this is when we use the central limit theorem. So since n is greater than or equals to 30, so that means the x bar, the sample mean, is actually normally distributed with mean equals to the mean of the population, and then the standard deviation sigma equals to sigma divided by square root n. Okay, so for here, the mean is the same. So the standard deviation will be equals to 30,000 divided by square root 40. So this one is equals to 4743.42. Okay, so basically this one we want to find probability of x bar, the sample mean, greater than 89500. Okay, I just give the final answer so you can try this one. So the final answer here is 0.9545. And then for B, we want to find probability of the sample mean x bar less than 100,000. So this one, the final answer is 0.7019. Okay, and then the last one, we want to find probability of sample mean, which is x bar, in between 95,000 to 99,000. So the final answer here is 0.3274. Okay, so try this by yourself. Okay, and then this one is actually the full normal distribution table for your reference. Okay, I think that's all for today. Okay, thank you everyone.